So, we continue with our discussion on fault modeling. So, you recall in our last lecture we talked about some fault model at the behavioral level, functional level and also the structural level. We mentioned at the structural level the Stuckert fault models are the most commonly used, and also bridging fault model is quite common in modern day VLSI chips where the wires are very close together. So, to continue with the discussion, we first look at today some switch level fault models. Switch level means at the level of the transistors. So, why we call it as a switch level? Because here we regard a transistor, a MOS transistor as an ideal switch. Like what I am saying is that suppose I have an NMOS transistor like this, let us say S and G, and this is S and D, source and drain, and this is the gate. And if I apply gate voltage equal to high, then as if this is a switch which is getting connected, there is a connection, this is S and G and D, and if G is 0, then the switch will be disconnected, S and D, it will be disconnected. Now, if it is a PMOS transistor, it is just the reverse logic. If it is a PMOS transistor, then if G is 0, then the switch is on, if G is 1, then the switch is off. So, in this fault model, we are assuming that the MOS transistors that comprise a CMOS gate behave like ideal switches, where source and drains are either connected or they are disconnected. Okay, fine. So, just as I said, an NMOS transistor is on when the gate is high, PMOS transistor is on when the gate is low. Now, here we are considering two different fault models. First is transistor stuck open fault, which means the switch is never turning on, source and drain are never getting connected, irrespective of the voltage we apply to gate. Second one is the reverse, it is short, the source and the drains are already shorted. So, it is always conducting irrespective of the voltage we apply to the gate. Now, the reason we consider these switch level faults separately is that you will see that the behavior of this circuit becomes very peculiar in presence of these faults. Like other fault models we looked at, like Stuckert fault model, which is said that is very popular, but Stuckert fault model cannot capture some of these transistor level fault models which modify the circuit behaviors in a very peculiar way that we shall see shortly. So, look at this stuck open fault model first. Here, as I said, a transistor becomes permanently non-conducting because of some fault. Now, we shall see that because of this fault, when I apply some input, the gate output may remain the same as it was in its previous state when the last input was applied. Now, what does this mean? That I have a, let us say, a combination circuit, a NAND gate or a NOR gate. Normally, for a combination circuit, when we apply some inputs, we get some outputs which is just a function of the inputs. But now we are saying that I apply an input and the output whatever I am expected to get will not depend on this input, but will depend on the previous input, which means now as if my combination circuit is behaving like a sequential circuit, it is remembering the previous state in some way, right. So, we say that the circuit exhibits sequential behavior, and because of this reason such faults cannot be detected by a single test. We usually require a pair of test vectors, which is sometimes called two pattern test. So, we shall see with an example how it is done or it is happening. But this two pattern test, sometimes in practice what is done, that we first generate the set of test vectors for single Stuckert faults then we rearrange these test vectors so that this 2 pattern test requirements are satisfied. So, let us take the example of a 2 input CMOS NOR gate and let us illustrate what we are talking about. Okay. Here we have a 2 input NOR gate. There are 2 NMOS transistors in the pull down and 2 PMOS transistors here. The output of this gate is driving some other gate or gates. Here I am showing the equivalent load capacitance. So, I told earlier that whenever a transistor is driving another transistor or another gate, so the gate capacitance that this line is facing, that is quite significant, and it is that load capacitance I am showing here. Normally for a CMOS circuit, every line will be driving 2 transistors, one PMOS and one NMOS, like A here is driving 2 transistors. So, this is the equivalent capacitance. Now, let us see, think of a fault in transistor T1 stuck open. See, for stuck open, I mean intuitively speaking, how I should try and test it? Well, I should test it in this way, that this transistor is open, let me see if a current can flow here. So, the only test vector I can apply for that is 0 0, because 0 0 is a test vector which makes both T1 and T2 conducting and VDD should be connected to the output. But if there is a fault, VDD should not get connected, right. So, I am expecting this, but let us see what will happen here. So, if suppose I apply 0 0, so in presence of the fault, or means let us say first in the absence of the fault, the output will be VDD or high, because both the transistors are conducting and both the pull down are off, 0 0 means both are off. So, the output node is connected to VDD, so the output is high, which means the capacitor is charging to its full voltage VDD minus this drop. Okay. But suppose I have the faulty case where this transistor is stuck open, then if I apply 0 0, I suddenly have a situation where my pull up network is not conducting because one of them is off. So, F is not connecting to VDD, neither F is connected to ground. So, the output node is electrically disconnected, it is like a floating wire, it is just floating. So, there is no path for this capacitor to get charged or discharged. So, this capacitor will be retaining the last charge that it was set with, the last value of F, whether it was low or high. Low means it was discharged, high means it was charged. So, it will remain in that capacitive state and the output value will show that same thing. The output is floating and the voltage will depend on the charge stored in the load capacitor. So, to circumvent this problem, what we do? We additionally apply another vector in the beginning 1 0. The target is to set the output at a known state, the reverse of this. I want to discharge the capacitor. So, if I apply 1 0, then my pull down network will be on, the capacitor will get discharged via this path, output will be 0. Okay. So, now if I apply 0 0, so in the faulty case output will remain 0, in the fault free case output will be 1, I can distinguish, right. So, I need a pair of patterns to be applied in a particular sequence. This is the characteristic, right. Okay. Now, let us come to stuck short fault. Stuck short is the other way around, where a transistor is permanently conducting. Now, we shall see again through an example that for this case just checking the logic value in the output may not be sufficient, because both the pull up and pull down network may be simultaneously conducting. So, you can have a situation where it effectively becomes like a voltage divider, So, it becomes like a voltage divider. So, you have VDD here, this is your pull up conducting resistance, pull down conducting resistance, and you are taking the output from here. Now, this output may be at a voltage which is between 0 and 1, VDD and ground, which may be neither 0 nor 1, it is somewhere in between. So, just by looking at the logic value, you really cannot distinguish, right. So, this is the scenario here. Because of this fault, both the pull up and pull down networks may become conducting. So, the output may reach some indeterminate level between 0 and 1. But one thing is true here, because both the pull up and pull down networks are conducting, there will be a high current that will be flowing from VDD to ground. So, to detect this kind of fault, we just cannot look at the output voltage level, rather we monitor the current. This is sometimes called IDDQ testing. We measure the current flowing from VDD to ground. So, the test vector will be such that it will cause a conducting path from VDD to ground in the presence of the fault. Like we take an example of a NOR gate again. Let us say we take the case of a T1 stuck short fault. Let us say we apply a 1-0 test vector. So, for 1-0 test vector, this is supposed to be turned off, this is supposed to be on. So, in the fault free case, there should not be any path from VDD to F, because this would be off, but because of the fault there will be a conducting path. But in the pull down network, this A is also turning on this transistor. So, what is happening is that there will be a conducting path like this from VDD to ground. There will be a high current flowing, because pull up is also conducting, pull down is also conducting. This is what is meant by IDDQ testing. We have to measure the current, right. Okay. Now, one observation is that in the present day deep submicron test technology, this IDDQ testing is becoming difficult to use, because the transistor leakage currents, there are so many transistors, billions of transistors in a chip. So, if you take the sum total of all the leakage currents, that becomes comparable with this IDDQ current which you are measuring. So, distinguishing between the short circuit case and the non short circuit case is becoming blurred. The difference in the current will not be that significant, right. So, this is one problem. So, the geometric level fault model, we are not going to detail. Here we are looking at the circuit description at the layout level. So, we regard the layout level as a collection of rectangular shapes. Like see means we have some information on the layout. So, we also know that which of the lines have more likely to be having bridging faults. Like say, let us say I have a gate, there are 4 inputs, but in terms of the layout I see that the wires are laid out in this order only. So, the chance of bridging fault are, let us say if A, B, C and D are there. So, there can be a bridging between A and B, between B and C, between C and D, but the chance of A and C or B and D or A or D having a bridging will be much less, because there is a wire in between. So, if we have some geometric information, you will be knowing that what kind of faults are more likely. Similarly, in memory, of course, here we shall not be considering memory testing, but let me tell you, in memory the cells are arranged in rows and columns, okay, very dense rows and columns. So, if we know which memory cells are near to each other, there is something called coupling fault. If you write something into a memory cell, the neighboring cell might get affected. So, you know which are the neighboring cells. So, you write something here and check whether the neighboring cells are getting affected, not the others, right. These are all examples of geometric fault models. So, these fault models can be derived directly from the layout. So, as I said, the memory fault models and also fault models for programmable logic arrays, these are some regular structures. These are all examples of this. Okay. Now, let us look into a very important problem. Now, we had looked at the Stuckert fault model, and we have said that Stuckert fault is the most widely used, in particular the single Stuckert fault. Now, for a circuit with let us say 10,000 lines, the number of single Stuckert fault will be 20,000, 2k, but still 20,000 is a pretty large number. Okay. So, now we see how we can reduce this number without sacrificing the quality of test. Okay. So, here we look at some properties of faults with respect to the gates, of course, that can help us in reducing the effective number of faults. This process is called fault collapsing, like some of the faults you can collapse into a single fault. We shall be looking at two different techniques or approaches, fault equivalence and fault dominance. Let us see fault equivalence first. The definition is very simple. Two faults in a circuit are said to be equivalent if the corresponding faulty functions are identical. Like the first example says, the input stuck at 1 and output stuck at 0 and output stuck at 0 in AND gate. Let us try to explain. You see, suppose I have a function, any block, the output is f. Let us say there is a fault in this function, the fault is alpha. So, in presence of fault, the output is f alpha. So, I have applied some test input, let us say t. Let us say I apply it to the good function as well as the faulty function. So, if I say that the XOR of f and f alpha equal to 1, which means it is either 0 1 or 1 0, which means they are different, then only we say that the fault is getting detected, right. Now, think of an AND gate. Let us take a 2 input AND gate. Let us say A B and F. So, if I have a fault A stuck at 0, your output F will be 0, because one of the input of the AND gate is 0. If I have a fault B equal to 0, then also output F equal to 0. So, if I have a fault F stuck at 0, then also F equal to 0. So, I can detect these faults by applying clearly a test vector 1 1, because here my fault free output F is supposed to be 1 and F alpha is 0, their XOR is 1. Right. Now, tell me one thing. So, in presence of the fault, the output will be 0. Okay. Now, if I see that the output is 0, so the output is coming to 0. So, can I distinguish whether it is a stuck at 0, B stuck at 0 or F stuck at 0? I cannot distinguish, because under each of these 3 faults, the function changes in the same way, it is becoming 0, a constant 0 function. So, just by looking at this output 0, I cannot distinguish between them. So, what I am saying is that, do I need to keep all these 3 faults? So, what if I delete any 2 of them and I keep only A stuck at 0? See, for detecting A stuck at 0, anyway I have to apply 1 1. You see, this test vector will also be detecting B stuck at 0 and F stuck at 0. So, I need not keep all 3, I will remove 2 and I will keep only 1, right. This is called a equivalence class. That is what I have shown in the slides. So, the first equivalent class is that input stuck at 0 and output stuck at 0 in AND gate. But if it is a NAND gate, that input stuck at 0 and output stuck at 1 will be equivalent, they are all equivalent, they will all make output equal to 1. For an OR gate, the input and output stuck at 1 faults are equivalent. For a NOR gate, input stuck at 1 and output stuck at 0 are equivalent, this you can check. and for a NOT gate there are two equivalence classes. Input stuck at 0 is equivalent to output stuck at 1 and input stuck at 1 is equivalent to output stuck at 0. So as I said, so if I can identify every such equivalence class, we keep only one fault from that class and remove the rest. This process is called equivalent fault collapsing. Like in the example I have shown here, we have kept only one, we have removed the other two. This process is called equivalent fault collapsing. Okay. Let us take an example. So, here I have shown a circuit. If we count, there are 16 lines 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, there are 32 possible single stuck at faults. I am showed them stuck at 0, stuck at all of them. What I do, using these dotted lines, I have shown the equivalent faults. Like for this AND gate, the output stuck at 0 is equivalent to input stuck at 0, input stuck at 0. These three are equivalent. Similarly, for this AND gate also stuck at 0, stuck at 0, stuck at 0. This AND gate also same. This OR gate stuck at 1, stuck at 1, and this stuck at 1. These are all equivalent. This OR gate also stuck at 1, and this stuck at 1. For this AND gate stuck at 0, stuck at 0, stuck at 0. So, what I am saying is that for each of these equivalent classes, I shall be removing, see, these are all 2 input gates. So, each class is containing 3 faults. For example, for this AND gate, so I shall be removing 2 of them marked as red, I will be keeping only 1. So, I will be repeating for all of the gates. If I do it, I get something like this. This was the original thing, the red marked faults I have removed by collapsing. I keep the rest. So, you see that after I have done equivalence collapsing, the number of remaining faults is only 20. So, earlier it was 32, now it has reduced to 20. So, this is a process which is typically done before we actually do testing of the circuit or test generation or whatever, right. Fine. There is another method using which also we can reduce the number of faults. This is called fault dominance. Fault dominance is a little different. The definition goes like this. It says, if all tests for some fault Fi also detect another fault Fj, then Fj is said to dominate Fi. We denote it like this. We are saying if all tests for some fault Fi detect another fault Fj, then Fj dominates Fi, and if such a property is there, what I can do? We can remove Fj. We keep only Fi, because we know that tests for Fi will automatically detect Fj, that is the definition. So, if we only keep Fi and generate a test for Fi, that will guarantee that Fj will also get detected. And if it is a mutual relationship, Fj dominates Fi and Fi dominates Fj, they are equivalent. Now, let us take an example. Like in an AND gate, the output stuck at 1 fault dominates input stuck at 1 fault. Let us see how. Take a 3 input AND gate. So, we define Fi as stuck at 1 fault in, let us say, line A, and Fj as stuck at 1 fault in F. So, for detecting stuck at 1 fault in line A, what are the possible test vectors? There is only one test possible, 0, 1, 1, because if B and C are anything other than 1, 1, output will be permanently 0. So, I want to apply something where B and C will be allowing the fault effect to propagate, that means 1, 1. These are the so called non controlling values that we had discussed earlier, if you recall, and A is the point where fault is there. If there is a fault, this will be 1, if there is no fault, I have applied a 0. So, fault free case output is 0, faulty case output is 1. There is a single test. But for Fj, which is stuck at 1 in the output. So, any test which makes output 0 will be a test for this fault, because I am trying to check whether the output is stuck at 1 or not. So, I can apply any one of these 7 vectors, they all make output 0, but if there is the fault, output will be 1 different, right. Now, here we see that the test for f I is a proper subset of the test for f j. So, I can remove f j from my list, because I know if I detect f I, which I can do by this vector is also included in the test set for f j. So, this is an example where f j dominates f I and I can remove f j. Okay. Remove f j and keep f I. Detecting f I will also guarantee the detection of f j. Fine. So, fault dropping is a process where we use fault simulation, which is a process we shall be discussing next. So, in fault simulation we detect or determine the set of faults that are detected by a given test set. Now, the complexity of fault simulation depends on the total number of faults. So, if you can reduce the number of faults, fault simulation can run faster. Fault dropping, what it says is that suppose I have generated a test for a particular fault. I carry out fault simulation to find out what other faults are also getting detected. So, if I find out that there are 5 other faults which are getting detected, so let me remove those 5 faults from the fault list. So, the size of my fault list will get reduced. This is called fault dropping. Okay. It refers to a technique where the faults detected by a test vector are removed prior to the fault simulation with any subsequent vector. Okay. Now, there is a heuristic which is available, which simplifies our process of identifying the equivalent and dominant faults. There is a heuristic called checkpoints. Now, checkpoints is defined as, for a circuit, the primary inputs and the fan out branches. Like in this circuit, the 2 input XOR function, the primary inputs are A B and the fan out branches are A1 A2, B1 B2, C1 C2. These are the checkpoints, C, D, E, F are not. So, there is a checkpoint theorem which says that a test set that detects all stuck-at faults on the checkpoints also detects stuck-at faults in this, all stuck-at faults in the circuit. So, the motivation is that we can use the checkpoint theorem as a simple heuristic for fault collapsing. Means in this circuit we identify the checkpoints, just keep the checkpoints and delete all the fault on all other lines, because you know that fault on all other lines will be either equivalent to some other fault or they will get dominated by some other faults. So, checkpoint heuristic is a very quick method to do this fault collapsing, right, and this is often used in practice. So, with this we come to the end of this lecture. Now, in our next lecture we shall be looking at the problem of fault simulation. Thank you.